Hi, welcome to worksheet number 9. This corresponds to section 7.2 on the textbook. We'll do more integration by using trig substitution. So here, first we'll just kind of review the trig identities, and we'll use that to find the integrals. So here, basic review of the trig identity. So the reciprocal means like 1 over something. So first we have secant x is 1 over cosine x. And then we have cosecant x, which is 1 over sine x. And then cotangent x is equal to cosine x over sine x, which is basically 1 over tangent x, because tangent x is sine x over cosine x. All right, tangent x, I guess I'll just write that out here. Sine x over cosine x. And then cotangent x, I wrote it there, but cosine x over sine x. And then the Pythagorean ID, this is cosine square plus sine square is equal to 1. So this one you definitely have to memorize. I'm going to highlight this. Cosine square, sine square is equal to 1. And then what we can do is we can divide everything by cosine square. So cosine square minus divided by cosine square is 1. Sine square divided by cosine square is sine over cosine is tangent, so tangent squared is equal to 1 over cosine is secant squared, right? So we'll use that. Let me just box this also. I'll use these two. So that means I can convert like sine square into cosine square and cosine square into sine square. Sometimes one is easy to find the derivative. So we'll use that property to find the integrals. And we can kind of do the same thing. We can start from here, divide everything by sine squared. So cosine over sine squared is cotangent. So I can say cotangent square x plus 1 is equal to cosecant squared. Okay, so we'll keep that in mind. So let's say I'll look at first example. We have sine square, integral of sine squared times cosine cubed. Let me just sidetrack a little bit. If I had just sine and then cosine dx, that'd be a little bit easier because I can let u2 be sine x, and then du will be just cosine x dx. Well, I see cosine x dx, so I can just go u du, right? So I can go from there. So if I see cosine and sine together, I can let one up to be u, and then the other one will be just cosine dx, and there's cosine dx, so I can go from there. Only problem here with the original question, example 1, is cosine cubed. So what I'm going to do that. If I didn't have the cube, if it was just cosine, then it'd be easy. I can let u to be sine and then go from there. I noticed that, again, as I said before, I can basically convert cosine square into sine square. So here, let me go back and say, well, this means cosine squared x is equal to 1 minus sine squared x. And I can kind of say the same thing about sine squared. So basically, this kind of allows us to convert cosine squared in terms of sine or vice versa. So this is what I'm going to do. I'm going to rewrite cosine cubed because I didn't like the fact it was cosine cubed. I want just cosine by itself. So I'm going to make a little side comment maybe here then. Cosine cubed is cosine squared times cosine x. And then I can use the fact that cosine squared is 1 minus sine squared. So that's 1 minus sine squared times cosine x. So then I just have cosine x. I don't have cosine cubed anymore. So maybe I can use that fact. So let me go back here. So this is sine squared times 1 minus sine squared times cosine x dx. So let's see. Instead of cosine cube, I wrote 1 minus sine squared cosine x. So that sine squared, I had it initially. So now I have everything sine and cosine and dx. Oh, that'll help us. So let u to be sine x, and then du is cosine x dx. So having said that, I can go u squared, 1 minus u squared, and du. Okay, hopefully this will make it a little easier to integrate. So u squared minus u fourth, 1/3 u cubed, 1/5 u fifth. So then 1/3 sine cube minus 1/5 sine 5. Okay, plus c. That'll be my answer. So my strategy here was kind of going back here. If I had just cosine x and dx a bunch of sine, that is the easiest case, because then I can let u to be sine and then du will be cosine dx. This question I need to take extra step because it was cosine cubed, but we use the fact that cosine squared can be turned into 1 minus sine squared, right? So I can break down cosine cubed into something with a sine in it and then cosine by itself. So then I can let u to be sine and then go from there, right? So that's going to be our strategy for when you have sine and cosine mixed. So let me look at the next strategy here. So it's just like what we did. One of the exponent is odd. So for example, if cosine has an odd power, then use cosine squared is 1 minus sine squared to peel off the power and have only cosine left, right? So sorry, it's kind of like weird explanation, but if I have cosine cubed, I can split that into cosine squared and then cosine, because I can convert cosine squared into 1 minus sine squared. If I had cosine to the 5th power, then it's cosine 4th times cosine, and cosine 4th is just cosine squared times cosine squared, so I can do 2 of these, right? So I can have it so that I only 1 cosine left. So from there, then after that, let u to be sine x, then du will be cosine x dx. Then it'll make it a little bit easier to calculate. Evaluate the integral. Same, if the cosine has an odd power, then you kind of do the same thing. So if sine has an odd power, then use sine squared is 1 minus cosine squared to peel off the power. So then let u to be cosine x, and du will be negative sine x, so it'll be like this. Okay. All right, let's look at one more example here. Next example, it says cosine cube. Oh, I don't see sine, just cosine, which is fine. Then again, I see the cube as the exponent, so I'll convert cosine cube into cosine squared times cosine x. That becomes 1 minus sine squared times cosine x. So this will be written as 1 minus sine squared cosine x dx. So I'll let u to be sine squared, sine x, and then du is cosine x dx. So even though I didn't have a sine, I noticed that it's cosine to the cube power, 3rd power. So then, okay, I'll split that into cosine squared and cosine, because I can make cosine squared into sine of something. So then I can make u to be sine x and go from there. So once I have it like this, then it'll be just 1 minus u squared du. So that's u minus 1/3 u cubed. So sine x minus 1/3 sine cubed x plus c, and that's my answer. Okay, here's this little things I have to be careful. At first I was like, oh, integral of cosine shouldn't be just sine, so shouldn't me just be, my first instinct was, can I just say sine cubed? But then this will be incorrect, because when I take the derivative, then I get 3 sine square x times derivative of sine, which is cosine x, which is not the same as this, right? So this is not exactly the same as that. So this, unfortunately, it doesn't work like that, because I have to use a chain rule. Anyway, okay, I'm gonna have you look at the next question. I'm gonna have you try number 3. Try 3. Pause this video, work on it, and then we'll meet back on the next topic. All right, if you're done with the example 3, let's look at the next one. They're going to use now secant and tangent. This is one of the identity we just talked about, and then also kind of review. Oops, this thing printed out weird. If I take the fact that if you take the derivative of tangent, you get secant squared. So somehow tangent and secant are related that way. So we're going to use that fact to evaluate our integral. Now let's look at example 4 here. There's a typo, I'm sorry. It should have been tangent for secant for dx. So this is a case where we have a tangent and secant mixed. Again, if I had secant squared, that'd be easy because then I can let u to be tangent and then, so let me just write that down. So it's a little sidetrack here. If I had tangent 4 times secant squared, then I can let u to be tangent. And du will be secant squared x dx. And we can kind of see there's secant x. So I can go u fourth du, so 1/5 tangent cube x plus c, right? So this would be easier case if I had just secant square and a bunch of tangents, because then I can let u to be tangent, and then du will be secant square dx is right there. The example 4, very similar, but unfortunately it's not secant square, it's secant fourth. But so we know that secant square can be converted into tangent. So this is what I'm going to do. I'm going to do a little side work here. So a little side comment is secant fourth, it'd be secant squared. Well, I need secant square because I want du to be secant square. I want to convert this into tangent. I'm going to use this identity, so it's going to be 1 plus tangent squared times secant squared, right? So I'm going to use that fact. So let me rewrite the original question. Tangent fourth from the original tangent fourth, right? Secant fourth, I'm going to write it as this times that. So 1 plus tangent squared secant squared dx. Yay, okay, now I have secant square and then a bunch of tangents. So I can let u to be tangent x, du is secant squared. So if I were to rewrite this, let me see, that's u fourth 1 minus u squared du. Conveniently, I have now secant square, and then everything else is tangent, so I can do that. So that'll be u fourth u6 du, so 1/5 tangent cube minus 1/6 tangent, I'm sorry, tangent 7th plus c. So that's my answer. So when we had tangent and secant, if I had the secant square by itself, that would be ideal because I can let u to be tangent and everything else can be converted into u. If the secant has fourth power, I could still get there because then I can use square into tangent, secant square into tangent, and then secant square, I just need one secant square. So that's going to give you the next strategy. We have tangent to the some power and then secant to the some power, right? Where secant has an even power, right? Like fourth power or sixth power. So what we can do is we can split secant into a bunch of power times secant squared. Secant even power, right? I'll need secant square for, I need it for du secant square dx. This one, if I have even power, this can be converted into tangent by using the fact that secant squared is 1 plus tangent squared. And once we have that, we'll let u to be tan x, and du will be secant square x dx. All right. And let's look at the next case where it's the other way around. Another idea we're going to use, again, is 1 plus tangent square is equal to secant square. We're going to use this again. But now I'm going to use the fact that the derivative of secant is secant tangent. right? So here I noticed that power here of tangent, they're both odd, so I kind of don't know what to do. But I need secant tangent as my dx, right? So if we let, so our strategy is here. If we let u is equal to secant x, then du is secant tangent dx, right? So secant tangent, so if they're both odd, then like, well, okay, then it becomes even power. So this is what I'm going to do. I rewrite this in terms of tangent 4 secant square tangent secant dx. Oh my gosh, it's kind of long. Why did I have to do it like so? Tangent 5 can be split into tangent 4 and tangent x, tangent 1, and secant cube is secant and then secant, right? The reason I want it this way, because if I let secant to be my u, then this will be my dx, du dx, du, sorry. So, okay, now I have, so my u is going to be secant, so this is fine. How do I rewrite this? So that's just tangent square squared. So a little side comment, tangent 4th is tangent square squared. Well, here I can say tangent square is secant minus 1. Secant, oops, secant minus 1 x minus 1 squared, right? So I can rewrite the whole thing. The reason I wanted to do this way is because I want to let my u to be secant, because this is my du dx. So I want to try to convert everything to secant. This is already secant, so I don't have to convert anything. This is tangent 4th, so I can do tangent square square. Tangent square, I can use this to convert that into secant. So, all right, so then I'm going to rewrite the whole thing. Secant squared x minus 1 squared times secant. That's a lot of writing. Let u to be secant x, and then du is secant tangent dx. All right, let me put it up a little bit here. So that means, oh, okay, I have this and this and this, this and this and this. So I can rewrite everything u squared minus 1 squared times u squared times du. U squared minus 1, the whole thing squared, u4 minus 2u squared plus 1 u squared. So that's u6 minus 2u4 minus plus u squared. So that'll be 1/7 u7 minus 2/5 u5 plus 1/3 u3. See? So that'll be 1/7 secant 7, 2/5 secant 5, 1/3, oh my gosh, secant cubed. Yikes, that's my final answer. So that gives you strategy when tangent has an odd power. We can use secant, let u to be secant. We need to peel off secant tangent dx, right? Then go from there. This is a kind of quick formula that you kind of want to know. Tangent is, we used sine, cosine dx to actually calculate the evaluate the integral. This before natural log of secant x plus c. So you can kind of memorize this part. And same for secant, as we can do natural log of secant x plus tangent x plus c. So I can kind of remember those two separately by itself. So when we have tangent and secant mixed, I can use one of the strategies with like even power and odd power. When you have tangent and secant by itself, I can kind of use that formula right away. Okay. Next, this one, if you look at number 6, try this 6. I'm having tangent and cosine. Well, I thought we're supposed to mix tangent and secant and sine and cosine. Here, what do they use tangent and cosine together? So if things are mixed, maybe a good strategy is to write everything in sine and cosine and see where it goes. So for this, my hint is rewrite this. I'm using the fact that sine is tangent is sine over cosine. So I can say sine squared over cosine squared cosine cube dx like this. And well, there's a cosine square and the cosine, so they cancel out. So it's sine squared times cosine x dx. And then I can go from there. Right. So sometimes it kind of works out if I convert everything to sine and cosine, and then somehow it does work out. So I'm going to have you pause and work on 6, try this 6 and try this 7, and then we'll meet back after that. All right, let's look at the next one. I'm going to actually skip this part. We'll skip this. It's pretty long, but I'm going to get to the half-angle formulas. These are two formulas or identities that help us to convert like sine square into just sine or cosine. So first one is cosine square x is equal to 1/2 1 plus cosine 2x. Notice that this is this and then this is this, right? So I can convert cosine square into something with cosine but 2x instead of cosine x. Sine square x is equal to 1/2 1 minus cosine 2x. Same here. I started from sine square, then I ended up with cosine 2x. So, all right, let's see if we can use that. So here, oh gosh, my integral sign never gets print out well sometimes. So here, cosine square, again, I cannot say antiderivative of sine square because when I take the derivative of sine square, I get 2 sine times cosine, so I get something different. So I don't like the fact. What I can do is I can use this formula right here. So I can rewrite it as 1/2 1 plus cosine 2x dx. Okay, so that means I can split the integral 1/2 cosine 2x dx. Okay, the first one is easy, just antiderivative integral of 1, just x. So x over 2 plus 1/2 times antiderivative of cosine is sine, so sine 2x over 2. When I take the derivative of sine 2x, I get sine 2x times 2, so that'll cancel this one out. This 1/2 is here, so then I get the, what do I get? X over 2 plus sine 2x over 4 plus c. That'll be my answer here. So this kind of strategy is convenient when you have like only the even power. I don't have any odd power, so I don't get the cosine d theta, cosine x dx to be du. All right, so let's see. So strategy is to use appropriate half-angle formula or identities. Okay. All right, I'm gonna have you try this number 10 and try this number 11. They're kind of basically the same question. Let's try this number 12. Sine squared, cosine squared, there's no like odd power, they're all both even power. So what can I do? Again, I'll make a little side note here. Cosine square times sine square. So again, it'd be 1/2 1 plus cosine 2x times 1/2 1 minus cosine 2x, which is 1/4. Oh, it's like a plus b, a minus b, right? So that simplifies to a squared minus b squared. So this is like my a, this is like my b. So it'll be 1 squared minus cosine squared 2x. Okay, so I can rewrite the original question into 1/4 1 minus cosine square of 2x dx. So that's 1/4 1 dx minus cosine square 2x dx. So that would be, this is just going to be x minus, I can use the double half-angle formula again. So cosine squared 2x is equal to 1/2 1 plus cosine 4x, right? We basically double this angle. When this was x, it becomes 1 plus 2x. If it's 2x, there's just double that. So it's just like a 4x. So I can say that's 1/2 1 plus cosine 4x dx. So that's that, minus, I'm looking at this part, integral of 1, again, it's just x, so it's a negative 1/2 x, but then there's a 1/4, that'll be just 1/8 x. And then, again, I'm taking the derivative, integral of cosine 4x will be sine 4x over 4. So if you calculate that out, that's 1 over 32. Sine 4x plus c. I can calculate this one out. That'd be 1 over x minus 1 over 32 sine 4x plus c. Yikes, it's long, but we're there. And I think I'm gonna skip this part also. So we might need it later, but I don't think I'm gonna skip it for now. And I think that's it for now.